Okay, so we'll move on to GIS, which is putting space into it, basically, explicitly. So GIS is used for quite a lot of things these days. It's increasingly being used by governments and marketing and a whole bunch of other things. But it's basically literally, in the old days, what we would have called maps, just getting a lot more data behind them. So the kinds of questions that you can ask about is literally the kinds of things you would have had off in the past, like what's the name of this place? Where is the city hall? Or in our case, where is Pippa Beach, which seemed like an eternal journey yesterday. What's the shortest route between A and B, which I'm not convinced the bus driver took, though he did take it at high speed. What's the, what kind of relations exist between different facets of data? So where do the roads sit versus where the people live, for instance? So in Tasmania, there seems to not be a very good correlation between the demand for public transport and where it actually appears, and a routing algorithm could help that quite a lot. And this is the kind of things you can do with GIS. But you can also do what-if scenarios. What if we put something there? How would the existing structures support that, or would there be gaps? And what's changed? So you can also go back in the past and look at past maps. So I forget who showed it to me yesterday, but someone showed me the image of the big tree, and I said, how did they know not to knock it down when they were building all those nice buildings around it? And they showed a picture, or someone said they'd seen a picture of only a few decades ago where it was beach and sand. So the tree had always been there and just built around it. That's why you can sometimes understand the structures that you see by building up through the past. As I said, it's used in a huge number of things these days, like transport planning, natural resource management, provision of services and utilities, mapping of census and demographic data, economic property mapping, a lot of military planning, and then into some of the biophysical sciences around particularly geology and habitats, and bioregionalisation, where you're trying to take biodiversity data and find effectively spatial clustering of the biodiversity. So, I don't know how many of you are familiar with it, but like the large marine ecosystems, the oceanic provinces by Sherman, nesting down at ever finer scales till you get to individual reefs. So you've got effectively clustering across those scales based on shared biological or physical properties. So the main parts of GIS are mapping and visualisation, which is where many people first get their introduction to GIS, but it's a whole more than that. There's the management of spatial data and queries around that, and actually doing a statistical analysis, but there's equally a large industry in the computing science world around how you store data and manipulate it and retrieve it in these database. Right now to automated mapping processes. So Chris is going to eventually talk. He's not just here as the big cuddly mascot for the whole the summer school. And in that point, we'll talk about how you engage with people. And one of the chief things that we find as modelers is that people are scared of models. They don't necessarily want to play with them themselves, but they might want to look at the output. But if it gets a little bit old, then they're not as interested anymore. So if you can have automated delivery of some of this information, so it's rapidly and repeatedly put up, they stay more engaged. So it all started with a guy that's known as the father of modern epidemiology. He's actually also the father of GIS. So what this guy did was, back in the 1850s and before, they thought that cholera was spread in the air, that you coughed on someone, or it was a vapour in the air that was evil and malicious and epidemic. He thought there was something deeper than that. And there was a big outbreak in Soho in 1854, and he sat down with a map and he marked on with his pen where all of the cases were happening. He also marked on the number of cases, trying to see if he could see patterns in it. And then the big leap that he made, so he was already doing GIS at this point, the big leap that he made was that he also marked on the water pumps. And he found that there was a water well right in the middle of it, where people would draw water and go back to their houses. People still didn't believe that waterborne virus was the source of cholera until he went and took the handle off the pump, and the cholera stopped from that area. So that's when they discovered how cholera was spread. There's even a pub now right on the spot with a handle on the wall and a dead pump in the middle of the room. But in this process, he's known as the father of epidemiology for doing this kind of modelling to understand the transmission of disease. But he was doing paper and pen GIS, which is how I had to do GIS when I started my career 20 years ago. When I did an Atlantis model to draw up my spatial 3D boxes, I literally had to sit down with paper charts and big pens and a ruler and measure out distances and stuff. So feel privileged that you have GIS to help you these days. What you guys can get done in 5 minutes used to take me about a month and a half. So the data can be highly multi-dimensional. It can be huge, which can get tedious if you're waiting for it to download to your computer, particularly if you're sitting in my hotel room, it feels like a presume. But the map retrieval to be really good at delivering information, which a lot of the online demographic sites now are, it has to be faster delivery, and that's where the computer science aspect comes in. So if you're going to do a whole bunch of GIS just for reporting to yourself and analysis, you probably don't need to worry about some of this detail. But if you're actually going to get to use it as a basis of delivering to clients and governance structures, for instance, you'll want to make sure you work with a GIS specialist to make sure your services are up to scratch and your delivery is up to scratch and you understand the demand you'll have. I don't know how many of you, it wouldn't have made international use, but Australia has a census every 5 years where they try to collect demographic information, snapshot for every place, every person in Australia. This was the first time they tried to do it online. They blamed a Chinese cyber attack for taking down the website. It was more likely they hadn't really thought about what would happen when 25 million Australians all went to upload their census report at the exact same moment. Once you've done all that data analysis, you have to then integrate. So this is why it's so good for the kinds of questions we have, because you can pull across different data sources. There are some other aspects that I'll get to at the end that are important to consider, but that's kind of the main part. So there's big GIS server processes that you can call upon, but in your own user options, there's kind of 3 options you've got. From there, which I'll explain in a minute, from there you manipulate the data to either do projections, to create your maps, to create your mapping. So when I do an Atlantis model, this is how I do all my habitat and geology, for instance. I GIS layer it up, I run the analysis, I spit it out, it goes into the initial conditions file. So you can, but if you're doing ecology, that kind of stuff, or economics, you can do basic spatial statistics. In fact, social science, any of the sciences can use it. And the analysis can be either qualitative or quantitative, so it can be purely bidding, or it can be highly complicated. The best part is that you get into these kinds of maps, and people are very visual, and in most of the world, maps are something that people get. There are a few exceptions where they just, for instance, there's one tribe that I think is actually in, I don't know which part of Amazonia it is, but they have no concept of a map in the sense that we would do, because it's just not how they think about their terrain, but they have their own spatial mapping. So the way that they project the data is different, but the basic concept of how you visualise the world that you move through is still fundamentally there for all of you. So this is an example of a web-based GIS. These are quite common websites now where you go, it's got the list of layers that you can add to the map, and you effectively make your own map of the system. So it loads all the data that you want by pointing and clicking over there, and then you can either extract the underlying data or save the map or whatever. The next most common one that we've probably played with is Google Earth, which actually is now Google's solar system. So this is a map of Mars instead of Earth, but it has that same process. It's like this literally loading up data layers. You can load in your own data layers these days on top. So it can help you do some basic analysis, and you can do fly-throughs and distance weighting and all that kind of stuff. The other good thing about this is you can drop in imagery. So for instance, when I do projections of what the future of a location might look like, so when so for instance, say on the west coast of Australia, I was helping them think about sustainable tourism futures. I could take Google Earth and the existing sort of Google habitat that they knew and were familiar with, and drop in extra hotels, or drop in an ecotourism resort, or more dolphins leaping, or whatever, so that they could get an image of what that future might look like. The most commonly used one, though, are GIS packages on your desktop. And so all of them kind of have the viewing space, and you put in your layers, and these are all the buttons for adding and doing analysis. These are the most common ones. The Esri ArcGIS is kind of the dominant commercial partner, but there are free ones, and the R-Tools, Paul's brought along a lot of the R-Tools for you to play with. I've got QGIS with me, which is a sort of a more GUI-oriented one, but they're sort of the most common free ones, and they've got pretty big community support. And you can see on this is just classified a single data set based on one property of it. So the basic idea behind GIS is that you have the data, you have the query that you're putting on it. So the thing that's going to pull out the map feature of your interest, they all interact with the geo database, which does its transformation and analysis that you're after, and then you get the map. There's different kinds of data though. So if this is the real world, there's different ways of summarising that real world to store the information. So typically on each one of the layers you'll have one topic area. So you'll have, say, geology in one layer, vegetation in another layer, human infrastructure like roads in a layer, buildings in another layer, number of people in another layer. So you separate out, effectively clustering the data beforehand. You're putting it into common topic themes per layer. I'll get to the different kinds of data storage in a minute, but the main attributes of each is that for each, whether it's a grid cell or a point, you have to give it its location and then its attributes and properties, like what's its projection, how big is it, what's the value of the actual piece of data. What that means is that there's quite a few files stored when you get a GIS. So shape files are the files that we talk about the most because it's the one you directly click on to open a GIS in a desk-based one. So whether it's Esri or QGIS, it's a shape file we think about. But it's actually a whole set of data together that define that database entry. So when you're sharing information that you've got out of the GIS, if it's not something you do normally, you need to remember that you have to send all of those files. The shape file isn't enough by itself. You actually need that combination of data because you've got the shape itself, you've got the projection being used, you've got the actual data being used, and then you've sort of got some infrastructure around that has to be shared. Okay, so the main kinds of data that you store in a GIS are continuous data, which can be very finely scaled or gridded. So these are rasters, so they're effectively lots of data points that create a grid or a big sheet of data. Or the other one is polygons, where there's literally lines and points of areas drawn, they're vectors that describe shapes and features. So they're the two main ways of doing it. So this is useful if you have got line features or the data's per feature. So it's often, for many things it's often less data intensive file size wise, but this is more how the scientific world tends to think about their data. So quite a lot of our data in the biophysical world at least will be stored in rasters. And the SDM, we were talking about raster data in the SDMs the other day. That's literally this kind of data. So the two ways that it approaches storing that information is if this is the real world, then the polygons draw on the shapes and associate that data here, so they would just say all of that area is one polygon with one value in it, which is that it's closed. Similarly with the river up the middle and the road can have a width attached to it, so the size of that vector or that line changes. Whereas when you get to the raster, you have to do some interpolation or some smoothing effectively if the features are changing very quickly. But in other areas where you've got, it allows for more resolution of things in the forest, for instance, so you can have a different value in each of those forest cells. So there's pros and cons to the different kinds of data representation schemes, depending on what you're actually trying to store. So this is an example. The very simplest kind of raster data is a photo. It's very easy to convey to people what's going on because they can recognise the photo. Just as a basic level, it's very simple data. You can load data in there though, so for those of you who think about doing net logo, for instance, what I've done is created a very simple net logo model that you can use as a template, and it uses a picture of your map for you to load it in. So the colour of the values in the picture, so where green is, for instance, that will become land, and where blue is the water. So that's a very fast way of loading in spatial data. It's literally to take a picture and then assign a meaningful value to the data. So when I load in, again from my west coast, for instance, of Australia, it's actually literally a map that people can look at that I use as my bathymetry load data. So the double value of that is that I can see what I've popped up. I had a process once where I couldn't figure out why the model wasn't working. It was because the guy was collaborating with a drawn vampire on it, just to see if I was paying attention. So you can see quite readily what that information is that you're trying to work with. But it also, there's heaps of algorithms for storing data. So the RGB values on the picture are a great way of storing data in a very compression-oriented way to transmit. So there's heaps of science, computer science that you can leverage on. You can also have other sources of data. So for the same kind of general area, I think this was from Texas from the example of the gentleman that I've used. He's pulled out the different road networks, he's pulled out the different usage networks, and you can layer up information on that. So you can, by having vectors, you can have multiple properties associated with that location. You can with rasters too, but it's easier in vectors to have multiple properties associated with each feature. And by having different data layers, so this is a street network, this is particular heavy use areas, and combining it with the easy to interpret stuff, you can get across to people quickly where the key features are. So the kinds of data available, this is a projection of a raster data set from the Great Barrier Reef, so you can colour code the value of the raster to give you the map and pull out features. So for instance, you can see the deep water channel running up through here and the coral reefs offshore. That's very good if you have fine scale resolution data. If you have sort of patchy data, so this is census data from the United Kingdom, you can also colour it based on attributes of that data. So this is based on the percentage of the population that's between the ages of 20 and 24. And this is showing relationship status. So what we can determine from that is that there's likely an inverse, that people in the 20 to 24 range aren't married a lot, basically. So you can start to see patterns already. And they don't tend to live with people that are married. They don't apparently don't want to live with their parents. Which my son realised that it's time to move out home. I love him, but seriously. There's also ways of classifying raster data. So that, for instance, this is raster data in Australia, where they've just classified it based on the number of people. Sorry, the raster data they've classified based on the, they've just done an SQL query and coloured it based on that. It has other, so you can do the same with vector data. So this is the suburbs of Sydney, and it's just based on what language you speak. The reason that this is really interesting is you can see that people are settling out based in their language groups and their ethnic groups. So while Sydney's a highly diverse place overall and pretty peaceful, there has been ethnic tensions in the past, and it's because it's been on a boundary point. So it helps people understand the processes that happen. You can also have point-and-click data withdraw from the website. So this is an example from the census data in Australia, where you click on a point on the map and it brings you up all the related attribute information for that location. So it's a great way of delivering information to people. It can also be useful for looking at change through time by building up the layers. So this is the Larsen ice sheet in Antarctica. And by building on the different GIS layers, you can look at not only what's there now, but how the ice sheet has changed through time. So you can look at where the data is fairly simple and not too complicated. You can layer up time dynamics pretty quickly. You can then go on to build different understandings from the one data set. So this was a paper in Science, I think it was, on cyclones, and they used the one set of data to understand very different aspects of the implications of that data. So they looked at the cumulative, so by layering up all of the cyclone tracks in history, first of all they identified places where there's a much higher risk of getting hit, so the cumulative energy locations. So if you're living in this area of the world, you're much more likely to get a high intensity outcome than if you're living, well, Borneo seems like a really great place to live. It does get a lot of cyclones, you think. It's also looking at the intensity field and how that can shift through time. So in some of the stuff that Laurent has talked about, he's talked about projections into the future. They're projecting where the cyclones will be, which can then help planning. So for instance, in Australia, the intensity field is shifting down the coast. So locations that in the past would never have suffered a severe cyclone and so didn't have to build their houses strong enough, now run a risk of getting a cyclone and having a problem. So the key ways of handling GIS is to think about the projection, which I'll get into in a second, the scale that you want to use in the map, how blown out or back, the kind of accuracy you're going to have to deal with. So, for instance, in Australia, was it 2 weeks ago, they updated our geolocation because since last time it had got 1.5 meters out, Australia is one of the fastest moving continents. And so they couldn't run Google cars in Australia because our geolocations were too off and they would run into things. So they had to update the geodata for Australia so that they could have Google cars. So this is about understanding your error structure. There's also consistency. There's quite a lot of times I've worked in places around the world where potential developments have been put on a map. And when you go actually out to look there, it's like, that's a nice piece of sand. Where's the whole village that was supposed to be here, that was supposed to be popular? So there can be map ghosts that you have to be a little bit wary of. So like with any data set, you've got to understand the errors and the consistency and the missing features. So just like you can have things that aren't really there, you can also have things that are missing so that they might have not bothered to record. Then you've got to, particularly when you're using raster data, you've got to understand the resolution. What's the finest pixel scale that you're actually seeing? The more that you have in either of these, so the tighter these are and the more of this you have, the more data you have to store that. So the last part, I think, is the projection part. So we live on a globe. It's not easy to transfer a globe onto a two-dimensional, like a flat field. So there's lots of different projections that you can do, and you get a different impression based on that. So this is the most common projection that we see in the world, where Greenland is pretty big and Africa is not so big. There's other projections that try to get the poles probably more representing what they are, but they blow out the tropics. And so it actually has a mental effect on the way that you think about the world. The way that we talk about the world in our brain conditions the way that we act about it. So in this kind of projection, ironically, it's easy to overlook the tropics and the role that they play in the system because we upweight the temperate and poles, ironically, where the major empires came from. And then, if you do this projection, it can drive home how central that tropical world can be. And interestingly enough, this is probably the vision of the world we might see. If we came, if we could leap forward 200 years, this might be the projections that we actually see more commonly in textbooks. When these nations like Nigeria and India and China, where the big powerhouses of population are, have a much larger role in the system. And maybe that the way that we look at the world, literally on the page, changes along with it. There's lots of different coordinate systems used in spatial data. The two most common are the latitude and longitude, but there's also the eastings and the northings. That can be a little bit complicated to get your head around, but you do have to be aware of that when you're trying to do projections. Otherwise, we all have fish on chili the other day when we were doing the SDF. So you have to be a little bit aware of that when you're doing the projections to make sure they make sense. And you have to confer that information when you're sharing data. So we had to try and do some modelling in Chile recently. They didn't tell us what their starting datum point was, they only gave us the relative change. So when we plotted it, it was kind of in the middle of Africa, which didn't make a lot of sense to us. So you have to be really careful about that kind of stuff too. The last part is that when you do data joining, so you can often have two different data sets that you want to combine together. So this might be the polygons that you've got with their IDs, and then you've got properties that you want to map to those IDs, and you might not want all of the groups, or you might want some of them. So you effectively create lookup tables, and from that you get your join data set that's classified that you can then export. That should be uploaded. What working with GIS does though is drive home to you that humans are good and bad at different ways of using visual information. In fact, far beyond just mapping, this is information that as scientists, particularly scientists who want to work with having engagement with people beyond science, really, really need to get their head around. This we do very well, comparing things on common scales or quite closely together. Using like volumes or shapes, we're not very good at. We suck at this majorly. If you want to convey your information easily, never use a pie chart, particularly a 3D pie chart, we're the worst at those. This kind of information is the absolute easiest. If you're going to use a coloured scale, don't do it for this kind of data where you actually kind of do this. Don't colour your dots based on intensity. This is only useful on maps for showing intensity on a map so that you can see where the hot spots and the low spots are. Do not colour your maps based on different categories. So as much as Microsoft would like you to colour things on slightly different colour scales per topic category, humans suck at that. If they're different categories rather than just in different intensities, use really different colour scales. The other thing is that at least 10% of your audience will be colourblind. So make sure you colourblind test your beautiful maps. Rainbows are absolutely the worst thing for colourblind people. They see about 2 of those colours. Hue blind people are even worse. But there are packages in R and other drawing programs and on the internet where you can immediately colour test the pattern that you're trying to draw. Red green is the worst. Red blue is pretty bad. Blue orange or blue yellow is much more effective. So make sure that you're aware of how people interpret the information you're trying to convey. Also think about how you're trying to represent information. So this is an example based on US data where they've just plotted up the same data but using different ways of doing the weighting. So this is looking at the multi-ethnic data, which is really skewed, and this is using quantiles, whereas this is using equal interval, which is kind of default in most packages. So completely no information content there at all. It's hidden all the information you want to know, whereas this is a much more useful way. On the flip side, the average age, because it's much more normal, any of the methods work okay. They'll get you some information. Though again, sort of quantile approach tends to report out the most information. So how you decide to bin up your data can be also very important. In my experience, things will crash on a very regular basis in all of the packages, so make sure you save often and back up and do everything imaginable, or you will be lots of swearing even if you're not Australian. There's often feature about failures where software doesn't do what you expected or has a memory of its own. Unfortunately, the best solution is still what you'll get from the average IT person. Turn it off. In fact, turn your whole computer off. Turn it back on and start again. Data availability is an issue I think we all face in all walks of life. There is an enormous amount of data out there, and spatial data, but there are some rules around some data. Some data can be commercially inconfident, some data, a lot of spatial data, particularly in the resource management world, has rules around those. So for instance, in Australia, I can't give you data that's resolved to an individual vessel or a location where only an individual boat goes to fish. I can only give you data where there's 5 boats gridded together. So I either have to grid things up into enormous boxes for some areas, or I just can't give it to you at all. So for Macquarie Island, there is only 1 boat. So for us to publish on Macquarie Island, we actually have to add a random scalar to our plots. We tell that's printed in the papers, we let the journal know what that random scalar is, but we can't make it public because it breaks Australian law. So there will be issues like that that you have to work your way around. There's also, it's an enormous topic area. I could go on for hours about how you do things. For the PDF version of this slide, the back end after the thank you slide will have a brief description of all the different features of a GIS, what you click where to bring up what kind of data and that kind of stuff. But really, Google or your favourite search engine is your friend. There's shitloads of people online that do heaps of GIS. So when you get stuck, particularly if you're using something like QGIS where there's a free forum, people will inevitably have hit your problem before, so just get on it out. And that's it. Okay, so is there any questions before we jump to the next person?